I can see the screen.
I can't read the text on the screen, unfortunately.
Okay.
Yeah.
Should we move the stand a little bit closer, or how do you want to do this?
Let's just restart.
Just do it on the computer?
Yeah.
Directly? Okay, so if you have to open the Zoom meeting on your
Yes.
Okay, we're going to change it around. Actually, we're gonna display the meeting, from the laptop that we have the presentation on to hopefully just screen share it so it, looks better. But you won't be seeing us, physically present up here though. So hopefully that doesn't take away from this, presentation.
Okay.
All right, so.
Sounds good.
Can you try yours?
Yeah, that should be good. Join computer audio.
Got it.
Okay.
Yeah. Can you hear us now?
Can hear you.
Wonderful.
Take that off screen share. Do not start the video. Why?
I wonder why.
I could possibly put mine on mute and then actually yeah, I can put mine on mute as you speak.
Okay.
That's great. But
Can you see my screen now?
I see your name there, Kaitis. I don't see any displays, any presentations yet.
Let's see. It says here that the host has disabled participant screen sharing.
Oh. Yeah, Sarah, I think you probably do let them share.
I'm gonna so you now have hosting abilities.
Okay. Let's see. How about now?
It works.
Wonderful.
Yep.
okay.
You can see it.
So the screen works, everything works.
Yes. Okay. Thank you everyone for joining us today. All right. Let's get started. Thank you everyone for joining us today. My name is Kaduz. I am a sophomore at Marymount University studying mechanical engineering.
And my name is Dino Foreman. I am also a sophomore and studying in mechanical engineering at Marymount University.
Okay. Last semester, we worked on a project, on an exoskeleton arm project, and the the inspiration for the project is an open source available educational kit called EduExo. It is fully available online with the design and the necessary materials and the instruction kit as a whole package, and that was the base for our project. And the objective of our project was to take the educational kit and modify it for another functionality. The project, the the objective that we had in mind was to use this educational tool as a tool for a physical therapy process. So for individuals was upper hand limb impairment, especially elderlies and people with physical injury. The physical therapy process is a very difficult process to go through. And yeah, the physical therapy process and also going through with their day-to-day activities is a very difficult task. So the objective that we had in mind was to design to modify and optimize this educational tool so that it can assist in the physical therapy process. Okay. So the we had a certain constraints and requirements that we had to meet for this project. One of the constraints is that in order for this tool for this exoskeleton arm to be functional, it needs to be lightweight. That means it should not impair the users or it should not impair the users or the client's ability to move their arm and their limb if any further than they are currently unable to. So one of the constraints is to make the device lightweight, and another thing that we had to consider was to make this to design this tool so that it does not limit their range of mobility. And a third constraint that we have to focus on was safety. That means components of electronic components of the arm need to be compartmentalized properly so that it does not have any shock exposure to the users. The designing Another objective that we had in mind was entertainment. So, like I just mentioned earlier, the physical therapy process is a very difficult and tedious task to go through. So, while going through the process, we would want to keep the users as comfortable and as entertained as possible. So, we had added an entertaining component to it. A game we had designed, well, not designed, the educational kit has a game design to it that was developed using Unity. So we have also integrated that same component from the educational kit into our modified design. Would you like to?
Course. Our justification for a final design of the EDXO was just simply based on its cost-effective ability. For this project, we wanted the ability to have it mass-produced in a way that would allow smaller income households to have the ability for a more developed physical therapy, as my member already said, or other exoskeleton that we wanted to use with the Elex EXO, but based off our engineering concept and design and our major points of, as my member said, entertainment, comfortability, and user-friendly process. The Alex EXO didn't help in any of those cases. It was well designed, but didn't fit our qualifications. That is why we use the EDXO specifically. For our phase 2, we wanted to finalize the research, make sure we had our electronics and physical parts ready. So we started to use CAD, specifically Fusion 360, to manipulate the parts that the EDXO gives you in the manual, to make it, as we've recently said, user-friendly. And of course, we do try to focus on a human design process. So in Fusion 360, we decided we needed better compartments for our electronics, specifically because we were adding a board to the EDXO arm to maintain the degrees of like elbow flexion, the game that we mentioned, which we'll get into a little bit later. There was another process of making the arm joint figure out the amount of force / newtons that you were applying to it to justify kind of like a high score system, trying to get better at using it as a either workout tool or physical therapy tool. So this was the elbow flexion point that we recently talked about. Can we change this over?
Yeah.
Thank you. This was the single arm that went across the bicep. For this, we wanted to add a secondary point for our electronics. Think over. This was the arm cuff. We wanted it to be a more portable and usable device, so we added a battery pack. We use this cylinder as our battery pack holder. Continuing on, back to the elbow one more. And this was our wrist mount for the board. The display in the center was an open sheet that had a little piece of plastic over top of it, so you can see or make adjustments as needed as well. For the old adjustments, it was just a single arm elbow flexion, no cable management or wiring could get through, so a lot of unsafe areas, especially when we had to solder together the wiring. There was going to be exposed wiring. The board would have fell out easily, causing damage to the arm as well. And also we had steel cable mesh to protect the user as well that we put in our design concept. For an assembly process, the wiring came with the instructions, but to use the board, we had to make a few adjustments. We did this design inside of Tinkercad and then moved it over into Fusion 360. That's why there's a sonar piece connected to it, because that's our design. That was our design concept as well, to change it over to the board. It had the same wiring method in a sense. For our coding and the exoskeleton function, we wanted tracking of the elbow flexion, so what position that you're moving in. For our force wall, that's when I was talking about the workout capabilities of the arm. Reading the position sensor was another possibility that we were able to overcome. It's just meshing together the tracking and force wall, so you can see how far the patient or user is going against the force wall. and our motor angle as well was kind of like a pushback feature to allow the arm to help or assist the patient slash user for physical therapy if their arm wasn't able to move at that point or needed help moving. All this code was provided by the original company for the e-NABLE in Unity, though we did have to make a couple modifications for the game, which was basically Pong, but downwards. So it was more like Space Invaders, and Pong had a child. The ball would move back and forth between two blocks that you have to bounce the ball off of to keep the ball into play. We coded some different backgrounds for it, and also coded like different objects for the game to get harder, so the ball might turn into more of a poly ball that you had to bounce off different angles to make the game more developed. Of course, the build and material list is here. Would you guys like to see all the parts, or are you okay?
I'm fine either
I'm
way.
very strong. You're all okay?
Yeah,
okay.
we can, yeah, get the big
Mm.
picture.
Continuing on, Caduce will finish up the presentation slide for our week 4.
Okay, so the final part of the project was assembling all the parts into one piece. That means assembling the product and assembling the product, installing all the codes onto the Arduino board, and then also connecting the Arduino board to the game that we had designed. And also, and as a final step of the process was testing if the game would work with the board or not. That was also another thing that we had a huge issue, connecting the board to the game. So the final stage of the project, which was also the most important one, was making sure that the game works smoothly as expected with the board. And let's see.
Unfortunately, this video doesn't have sound, but directing your attention to the deposit here.
Okay, so what we're seeing here is that the readings that we were getting from the exoskeleton arm, this was the readings from the position reading sensor. That means we were able to successfully track the position of the arm as we were moving it. This was the final product that we had for the arm. This was the this is what it looked like at the completion of the design. Gavin, stuff.
Yes. For the week 5 milestone, this was more a view of our data observation, our teamwork, and our conclusion of the e-NABLE, which is just very fast pace of a conclusion of this presentation. For the e-NABLE arm as well, for the final stage, we did have a tinier ESP32 board that did fit into the sleeve that was able to connect to Unity as well. For this system, as my member said, as my member said as well, the Unity process was a lot harder than it needed to be, especially because when we added the few features, since we were stepping into a little bit of unknown territory, the board didn't want to collaborate with the ESP32. We had to upload a couple of special systems inside Arduino to allow the board to access. There was another problem with the coding of Unity, but all were solved at the end for it to be fully operational. We can grab the system as well to show you it in person. Unfortunately, over the summer, while things were being moved in the classroom, it got damaged, of course. But this was the full arm with these straps attached to it as well. The motor does still work and is fully operational. We just need to plug it up to the board.
Also, let's see if I can. For ping pong, for the game, this was the game that we had designed. So if we were to play it on the computer, this was when we played it on the computer, this was what we had. Let's randomize it and go. This was the game, and the issue that we had was trying to move the bar using the exoskeleton arm. So connecting the board to Unity was the difficult issue that we had. But at the end, we were able to successfully connect them and play the game with using the arm. By moving the bar using the arm. Unfortunately, the board is damaged, so we cannot demonstrate how to play the game right now, but we're able to successfully connect them.
And I believe that will conclude the meeting as well, the presentation. Can you stop screen sharing? Are there any other questions about the board that we would be able to answer?
Just a quick question, but what exactly causes the bar to move? Is it just flexing the arm that causes it to move left and right?
No, it would be the 4-point servo that's connected towards the arm. It reads the digital and analog movement of the arm and spits it out as a controller in Unity. That allows it to read the analog system of the position tracker in Arduino, and also the force and position tracker, I believe, to use it for the workout / physical therapy aspect. Just move the bar in left and right, so the negative that you possibly saw inside the Arduino video is going to, of course, move to the left, and then the positive side, positive numbers that will be spit out is going to move it to the right. It was translating that over into Unity for the controller. That was our biggest problem, as we've recently said. Is there any other questions regarding the breadboard aspect of the controller, or any cable management issues that you might see?
So
No.
I had a question more than a suggestion. So the sensors were, you had, I think, a position sensor to sense the position of the, excuse me, of the elbow, and then there was a couple of other sensors, right?
Yes.
What were they used for?
The position sensor was to track the degrees of the elbow. So we use a special formula that was formatted inside the instructions to spit out the angle of where the elbow was. This was the starting position. So if we were to go back, it would go into the negative direction. If you would go up, it would go into the positive direction. The force wall was just to kind of force the servo either forward or back to wherever the elbow flexion needed to be for it to work in physical therapy. So if your arm like hydroprofilates like backwards, you can kind of use that force sensor to help the elbows joints. The position and tracking force wall was mainly for the physical therapist side of things to make sure that they can track the improvement of the elbow flexion / joints that were needed.
Yeah. So basically, we had two major sensors that we used. One was the servo motor. The servo motor serves as a motor and also as a sensor. It senses feedback from on the position of the arm. And also the second sensor that we had was over here, the strain bar. It was the it is the sensor that measures the force that is being exerted, and it is also the sensor that that we use to create the force wall. So yeah, these are the two major sensors that we used.
And the force wall is a force exerted pushback to the user. Is that what you mean by
Yes.
force wall?
Yes.
Basically, it's a way of us pushing the user to push their limit of movement. So in order for them to be able to improve their range of motion, there needs to be some kind of pushback force on their arm. So that's what the force wall is used for.
And of course,
Did you-
the opposite of it as well, to help the patient move their arm as well.
And you implement that by changing the stiffness on the servo or something, or
Yes.
how do you implement it?
The force that's going to come from the force ball that's being read inside Arduino, which allows the servo to give enough force towards the arm to either withhold the arm back to whatever position it's trying to move into, or help the arm move to the position it wants to get to.
Cool.
Is there
So
any other questions? Oh.
Sorry, John, or I have a few more questions, but if there are others, please go ahead.
Yeah,
Okay.
I'm just sitting in here from the UK. I tend to work with high school students, and we're working on prosthetics there. So I just dropped in because it sounded interesting what you're doing. Do you work with? Are you done sort of trials with this with the physiotherapists themselves in terms of the development of the product?
Unfortunately not. We were trying to get a physical therapist to kind of either do a video call or come in, but during the time of finals, unfortunately, we weren't able to have that time constraint moved in. It was by the time he would have been able to get the meeting, we would have been at a school and not had the product in hand. So unfortunately not.
Yeah. Are you planning to get some like feedback from that particular sector? No.
Yes. We are also kind of working with like Unity to do demonstrations with the robotic arm as well, or exoskeleton arm as well, placing it with its Unity Baker. So like doing different arm size testing, because this is kind of we can change the dimensions in Fusion, of course, but it's trying to get that one size fit all and adjustments for the arm in the future.
Yeah, so you say the plan is to sort of make it flexible to cater for different sizes of arms, yeah?
Yes.
Yeah, that sounds good. Yeah, okay. Yeah, that's thank you.
So is there, to follow on that, those questions, is there a plan to continue this work with the next generation of students in the lab, or where does this go from here?
Absolutely.
Okay.
For the next generations in the lab, we have kind of planted a little bit of seeds inside some students' mind to venture off and make their own exoskeleton arm within the EXO line. Some things that we wanted to do in the future as well is, of course, as I said, make it more flexible for adjustments. For the board, we wanted to get a better board because it was only about like, what was it, 18-bit?
Yeah.
Like OLED board that I was able to do. So getting a higher definition board so that you can use the game inside Unity, the Pong/Space Invader game, on the go. So you're able to use this in your own home without needing a physical therapist there, always. And for the physical therapist to track your movements/progress while they're still in their office doing whatever they need to get done. So
Wireless control.
wireless control as well, just benefiting
Yeah, so these are some of the features that we've thought about. Wireless control, being able to control it from a computer instead of checking on the arm. And also another thing that we have been thinking about was adding a neural reading sensor to it so that it can be able, we would be able to use it as a robotic arm instead of as an exoskeleton arm. So that's a possible improvement that can be made to it. And yeah, it could be done by us, or it could also be done by other students. The initial work for EDU EXO is available online, as I mentioned earlier, and also our work, the designs and the codes that we used for this prototype is available on GitHub. So we can share that file, and any engineering student here at Marymount or anywhere else can continue our work. It's available.
Sounds good.
Mhm.
So I think I saw a link, note from Eric. So there's a company, this company actually makes that exoskeleton arm. They produce it. Did I get that right? The EDU EXO arm, is there a company that makes that, or?
yes, there's a direct company that does make the EDXO arm and instructions themselves.
It's a company called Oxivo. I think it's based out of Europe. Yeah.
Right. Hey, Eric,
Oh,
you're here.
I ran out on my meeting early. I put a couple things in the chat that might be.
I saw those.
Yeah, so the company is Optivo. They have an updated version of the exoskeleton. And we do have a DPT program here. And they kind of tell me what they want out of things. And they're afraid of the current version because it's too many wires and looks too complicated. They want something that looks like a finished product. So that's what we're kind of working on and trying to get it wireless, right? And now apparently we can't use Unity anymore because Unity lost their minds with charging people. So I guess we'll switch to Unreal or something. I don't know. Yeah, 20 cents per install, and trust us, we know if it's pirated or not.
Yeah.
They were kind of crazy. I don't think we would ever get up to the threshold to owe them anything for something like this, but yeah, I think we've learned we need much better motors to kind of move this beyond, right, this prototype stage, because it's not strong enough to lift anything up really. If you wanted this to be a prosthetic bionic, you need that stronger motor. But it is, I think John mentioned that you were an educator in high school. I think it's a great platform to really start teaching people this.
and show them the basic principles, and their educational materials are really good at breaking down how it all works, the physics that goes into it. And they sell a complete, I think they have a much nicer kit now. It looks a little cleaner. But a couple of those and I think you'd be in good shape. I did have some high school students build this during a summer course. It took them a day, beginning to end, to finish the whole thing. That was a long day, right? The day is 9 a.m. to 5 p.m. And I 3D printed all the pieces in advance and held their hands and walked them through everything. But that gives you an idea of how quickly you could get it done with a lot of hand holding, or I guess with Caduce and Donnell, they did it in 6 weeks, which is pretty good. And they did a lot of adjustments and tweaking and changing boards and making magic smoke and recovering from magic smoke. So
Not more trial and error.
Yeah.
Any other questions or anything?
I don't have any questions. This is great. This is really nice, good stuff. Congratulations.
Thank you.
Thank you.
Well done. Yeah, good stuff. Yeah.
Thank you so much.
Thank you so much for your time.
Thank
You're
you.
welcome.
for your time. Thanks for doing this. Appreciate it.
Congratulations. Congratulations and good luck on this. Like, I just got my bachelor's like 2 years ago, and so it's fresh in my mind just how intense it is working on these kinds of projects while balancing classes. So.
Yeah.
And being stuck with a crap professor.
That part is arguable, but
I just sit around in my office with toys.
I suppose that concludes the meeting.
Yeah, I think so. If anybody has
Thank you.
questions, they're welcome to contact me on the hub. Or if you watch it later on, you can email me, leebubar@Marymount. And I can get you in touch with Caduce and Donnell.
Sounds good.
Thanks, everyone.
thank you
Thank
so
you.
much.
Thank you so
Sarah.
much.